Good day, everybody. Thank you very much for joining us today, and welcome to this technical webinar about enhancements introduced in the G3-PLC standard, enhancing the performance in dense networks. So last year, we in the G3-PLC Alliance introduced hybrid PLC and RF communication. And this year we opened the certification for hybrid devices. And I'm glad we can say that already many hybrid platforms have been certified. And now we also have the first hybrid products being certified. But of course, we also keep working on the PLC side of our standard. And we are very pleased to welcome you all this morning to this session about dense G3-PLC networks and the enhancements we made in the standard this year. My name is Leon Vergeer and I am the General Secretary of the G3-PLC Alliance. And today we have 4 experts joining us to explain you all about the recent enhancement in the PLC standard for dense networks. That is Cédric Lavenu from EDF, and who also heads the technical working group in the Alliance. Matteo Ferresio from ST Microelectronics. Kevin Jones from Renaissance is joining us, and Greg Tseng from Vertexcom is one of the presenters today, and they're all very much involved in developing the G3-PLC standard, so they should be able to answer all your questions about the developments. So what's on the agenda for today? Cédric will start with an introduction and the challenges in dense routing. Then Matteo will talk about enhanced routing with jittering. After that, Kevin will explain the Trickle algorithm, and then Greg will present the enhanced route request mechanism in the G3-PLC standard. Following that, there should be plenty of time to answer your questions. It will be a quite technical session this time, but in the discussion at the end, we can also discuss and answer more general questions you may have regarding G3-PLC, of course. And if you have any questions during the presentation or at the end, you can post them in the question box on your control panel. Afterwards, we will share the presentation with all the people attending. We will also record the session and share the recording with you as well afterwards. So I think that's for the introduction. Then Cédric, let me hand to you for the first presentation.
Yes, sure. Yeah. Good morning, good afternoon, everyone. So I'll also then share my screen. Oh, okay.
Yeah, please put it on full screen if you can, Cédric.
Yeah, it's
yeah,
now it is.
Yeah, perfect.
Okay, so what I will try to do this morning is to introduce really what a dense network is and what the challenges are that we have now seen in the network after, let's say, in the first deployments of G3-PLC, where we gained more and more experience. So what is really a dense network? Here I will tell about my old experience on something like A deployments, right? So in what we consider a dense network is basically a network that gathers more than 300 or 400 nodes. And what happens in these type of networks is that we start to see some specific behaviors, right? Specific behaviors can be observed. As I said, this is also for mainly, it's valid for both Semanic A, FCC, and other band plans. I would just say that the numbers that are shown here, it's for a specific Semanic A deployment, as it's one of the questions we had before that we received before starting this webinar. So what is to be noted is that in dense networks, it's of course easier to reach the capacity limit. As soon as traffic increases, as you have more nodes, you have more links, you have more neighbors, your G3-PLC network tends to be, let's say, heavier loaded than any small network with only, for example, 50 or 100 nodes. So this is really what we mean with this term. And as said before, in the field, we really saw this different behavior starting from a certain network density, let's say. So what we can observe, for example, in a real 800 node network, so it's a specific example. We made the analysis using a sniffer that has been installed close to the medium voltage to low voltage substation, so next to the data concentrator. In most of the smart metering deployments, that's the topology that is favored. And what we see when we look at the percentage of packets that were received by this single node, of course, it's not a global overview of the network because you only can hear what happens from one point of observation, which is close to the data concentrator. What we see is that basically load-ng packets are very, very predominant in the different packet exchange, and more specifically, the broadcast route requests that are used to build the routes are representing more than 50% of the packet capture. You can see here that the other packets such as beacons or 200 responses were representing less than 10% together. And application layer, the DNS COSEM, which is the smart metering application protocol, only represents 3%. We also have bootstrapping. That is, of course, needed for a device to join the network, is about 2%. So we really see that load-ng is dominating this. I wouldn't say that this is unexpected. I mean, load-ng is designed to work thanks to a flooding operation that will allow you to build the best route possible. But still, in dense network, there is some improvement, and that's what we are also trying to present you here. So when we look at the basic flooding operation, this is represented on the upper right side of the screen. You see that each node, for example, the node which is node A here, each node sends broadcast frame to all its neighbors, so the route request basically, which is then in turn repeated by all the destinations of the transmission from node A. So it means that all nodes in the network will technically repeat the packet, the route request at least once. This will, of course, it's in a dense network, this would of course create collisions. Some route request packets will not go through the network to the final destination. Some others will indeed do the whole path to the destination. But at the end, the bigger the network, the bigger the flooding, let's say. So you will really have a lot of route requests. And so as we have this rule for all neighbors to repeat the same route request packet at least once, and when we consider, if you look at the pictures on the lower part of the screen, when you see a typical deployment, so this is the 800 node topology on the lower left side. You see that at the end, if you analyze how the network is structured, you see that you basically have clusters of nodes with some attenuation in between, right? You can already see it in the original picture, but at the end, when you consider a node, a topology with clusters of nodes, then you can question whether there is really a need to pursue the basic flooding operation as it is defined today. Wouldn't it be better to only forward the packets, the route requests in that case, that maximize the chance to build routes of a stable length? So you would basically forward route requests only with a certain level of route costs, so a certain level of quality. And you could also imagine that if you have these nodes that are gathered as clusters, is there really a need that each single node within each single cluster repeats the same route request packet? So this is the first, let's say, the first idea to start improving the broadcast propagation of route request messages. And as you will see, at the end, for data broadcast packets, the question and the observation would also hold true. So indeed, when we see how data broadcast is done, according to the latest, so to the 2017 G3-PLC specification, according to this document, as for route request packets, each broadcast frame, it is identified by a certain header, which is called BCO header, so sequence number. So each device keeps track of the data broadcast packets that have been sent or have been, let's say, have been received in the neighborhood, and will repeat at least each packet, or at least and at most only once, right? So same as for the route request propagation, there is a lot of room for improvement. And that's what we are trying to show you in the following parts of this presentation, of this webinar. Just a quick overview before we get in the technical details of the mechanisms that have been consented within the G3-PLC Alliance. I'd like to give some updates about what has been published. So this year, in June 2021, we have published an internal specification of G3-PLC that includes basically all the enhancements presented today, and also all the changes that have been made to the specification up to now, some corrections, clarifications, and also the hybrid profile that Leon has mentioned in the beginning of this webinar. And by the end of 2021, we will include also enhancements related to the radio frequency part, with frequency hopping, last gasp features, and also the additional frequencies, right? So the specification also goes together in parallel with the certification plan, where the June 2021 specification will help the G3-PLC Alliance will base a new certification program referencing this 2021 June specification at the end of this year. In 2022, we also expect a new certification version, including the enhancements done to the radio frequency part. Also, something to note is that during this process, we also regularly reach out to ITU to update the ITU-T G903 standard with let's say with the features that have been published internally to the G3-PLC Alliance. So in 2021, we had an ITU-T G903 standard that adds the hybrid profile, and in 2022 we will basically base this publication, we will revise this publication based on the June 2021 specification, plus all the enhancements and additions that have been made by the end of this year. All right. We should also mention that workshop 1, so the technical working group, is currently working on other topics as well. So there's the possibility to make some improvements in the FCC band for power line communication. We also work with the LMS User Association to update the COSM in the fast classes to reflect the ITU-T publication along time. And we always are trying to address the questions coming from the market with respect to the issue they may have, to the question they may have, how to upgrade G3-PLC, and guidelines, user guidelines, basically are edited by the G3-PLC Alliance. So that was just a quick reminder of what is done. But I think we can now give the floor to. So this is Matteo, right? You're doing the jittering. So
that's right.
That's right. The screen, and Leon, I think you can hand over to Matteo.
Yeah,
thank you.
I'm handing to Matteo now.
Okay, I guess you can see my screen.
Yes.
Yeah.
Okay. Okay, just 1 second.
We can hear you and we can see your screens, Matteo.
Okay, great. Okay, so thanks everybody. Matteo is speaking, and I've been working since 2012 in ST Microelectronics inside the smart grid application team. Today I'm going to describe you the enhancement we made to the LoadNG routing in dense network scenario. So we're going to talk about what we call route request jittering. It is the first improvement we made to address the challenge that Cedric mentioned before in a real dense network. Let's maybe start with a brief overview. Probably who is already familiar with G3 protocol is already aware about those details. Just a brief introduction on LoadNG. So LoadNG, first of all, it is an acronym of the lightweight on-demand ad hoc distance vector routing protocol next generation, and it is specified in the G3-PLC specification within the Annex D. So this routing protocol is working through some control messages that are sent in the network. Those control messages are the route request, the route replies, and route errors. Some key aspects that I would like to underline of this routing protocol is that it is a reactive protocol. So the routes are established only if there is data to send. So let's say that the control messages are not sent periodically. They are sent only if there is the need to create a route or to send some data from one device, one node to another. Another capability of this routing algorithm is to to locally repair the mechanism. So let's say we have a route in place which is involving more than 2 nodes, so it is not peer-to-peer, but there is some forwarding in the middle. If there is a link which breaks in the middle of the route, the intermediate node can repair the route in a transparent manner to the sender of the data packet. And also the LoadNG is able to handle unidirectional links. That is something that can happen in the PLC world, as you know. Okay, so now let's see how it works in practice. We have a simple scenario. We have some example of how the LoadNG works. So we see in this example we have the node A who needs to transmit some data to the destination. The final destination is the node Z. So first of all, the node A sends a route request. It is a broadcast message. So this message will be sent to every node in the network. And in a real network, it will probably happen that the destination will not receive the message directly from the originator because it may be far away. So in this example, we see that the node F instead is getting all the nodes, for example, B, C, E, M. Okay, we focus our attention to F, is getting the route request from A, and it is computed the route cost to the originator of the message. Then the next step for the intermediate nodes, so for example, like F, is to propagate again what we call flooding. So it is a broadcast message. Each node in the network has to update the message, adding its own route cost, and propagate again the message. In this example, we see, for example, in this slide, we see F is adding its route cost to the route request and send again the broadcast message all over the network. For example, the route request will be received from K, and on route request reception, K will update its internal table because at that point it is aware of how it can reach the node F and also how it can reach the originator. So it is the node A. When finally the route request reaches the final destination, the final destination replies to the originator with a unicast message, which is called route reply. So in the reality, the final destination, so Z in this case, will receive more than one route request. It will receive maybe plenty of them, because I said before, every node in the network propagate the route request. In this case, Z chooses the best one, so the route request received with the lowest route cost, and it generates a route reply to the originator. So this route reply message, this time is a unicast message, will be sent back along the selected path. So in the example we saw before, we see that there is Z sending back the message to K, and then F and A. Once the route request is sent again to the originator, all the routing table in the intermediate nodes are filled up with the necessary information to send the data. So all the nodes inside the selected path will be able to send the data to the two endpoints. Okay, now I think we can see the weakness we identified in the scenario of a dense network. Okay, so we said before that the route request messages are spread by every node in the network. So also in the figure we have here, we see that A is sending the first root request message. Then all the nodes receiving this message have to increase their adding their own root cost to the message and propagate again the network. If we have a look to this example, we see that many nodes are receiving the root request from A, but the best one, the best link in this case, it appears to be C. Okay, but due to the fact that the messages are sent in broadcast and they rely only on the CSMA to be transmitted. So what can happen here? And in this example, we see it happening. It's happening on the node C. Is that sometimes the root request in a very large networks cannot be transmitted because they can collide with other root request messages, or also because the transmitter is sensing the channel and it detects that the channel is busy for several times. So it may happen that, like in this case, in this example, what we believe is the best root request, because it is the one with lowest root cost, get lost. And let's say we don't want this. We would like to have the best root request propagated along in the network. Let's have a look to how we addressed this issue. So the idea was to add a controlled delay, or jitter, to be applied on an intermediate node that is forwarding the root request message. The idea is for the intermediate node that is forwarding the root request, to put the root request in a queue for some time. Meanwhile, if it receives a better root request, so a root request with a lower root cost, it will then discard the previous one and will transmit only the best one. Now I can explain how this delay is computed, because it is not a fixed delay. This delay is based on the LQI. Basically, this delay is computed based on the SNR of the received root request. So an intermediate node receives a root request, compute the SNR on the received frame, and based on that, it computes the delay it has to wait before sending, before propagating the root request. This delay is quite high in case the SNR was very poor, because as we see here in this diagram, because we don't want to propagate root requests that are traveling across weak links. At the same, on the other hand, it is lower, but still quite high. Also, when the SNR is very high, because we don't want to transmit immediately those kind of root requests. Because here probably the SNR is so good that the root request maybe is coming from a node that is really close to us, to the receiving device, and we don't want to create routes with a large number of hops, because of course it is adding latency to the system. The jitter, or the delay, is null, so it is 0. It is the ideal case, the best case, let's say, when we are in the middle. So we received a reliable root request, but coming from a device, a node that is not really close to the receiver. Applying this jitter, this delay to the load ng, we reached two goals. First of all, we lowered the flooding. So there is a smaller number of root requests traveling in the network, because as we can see here, the nodes that have to forward a root request wait for some time before sending the message. In that time, during this delay, they maybe receive other root requests. So instead of sending like 5 or 6 root requests, they send only one. And also another effect is that as the delay is smaller when on what we consider the good root request, we give a higher probability of forwarding to what we believe the good root request that at the end will be part of the selected route. Okay, so this mechanism has been tested in ST laboratories, and the test setup was composed of about 100 nodes split in 10 groups. So more or less each group was composed by 10 devices. And so at the end, we have like those 100 nodes separated in different groups, and between each group, we added a variable attenuation. So we tested the system, adding 0, 10, or 20 dB attenuation between each group. Now, I'm going to show you the last slide, which is reporting the test result. So as we said before, we have 3 topologies: blue 0 dB, red 10 dB, green 20 dB of attenuation between the groups, and we tested 3 use cases. So the first one, use case 0, is without jittering. So it is the default behavior of the load engine. And then we tested 2 different versions of the root request jittering based on a different set of ADP parameters. What we have seen is that, the metric of this test is the average number of root requests received by each node in the network. And what we have seen is that applying jittering, we got a strong reduction of the root request traffic, up to 60%, for example, here, when applying jittering. Of root request reduction. And if we think about the numbers explained by Cedric at the beginning of this presentation, I think it is a real good achievement. Thank you.
Thank you very much, Matteo, for explaining this. So if anybody has any questions, please post them on the control box. Matteo, before we move on to the next session, a few small questions. So you mentioned a delay introduced by the jittering. Can that cause any problems as it adds latency in propagating the route requests?
Okay, thank you, Leon. This is a good question indeed. Well, no, it does not represent an issue because let me come back to this slide. It's true. Adding a jittering or delay when the root request is propagated will slow down a bit the propagation of root requests. So if node F, for example, has to forward the root request, it has to wait a bit more than what is specified in the original LoadNG version. But in the specification, it is also said that the final destination, Z, has to wait an amount of time before replying the root reply. By default, it is 4 seconds, the specification. And so even adding some delay, the final destination will still reach the root request message in time. And even if it does not receive the root request in time, the final destination can send a first root reply. But if afterwards it receives another route request, which is better than the previous one, it can send a second route reply. So there is no limitation on that.
All right. Thank you for answering that question. Then I think we should move on to the next presentation. Kevin, I'm handing for you to that. Yeah, perfect.
Okay, so you can see my screen.
Yeah, can see it.
Okay, well, welcome everybody. My name is Kevin Jones. I'm an applications engineer working for Renesas Electronics in Europe, and I'm in the Connectivity Solutions department, where I've been focusing on power line communications and the associated protocols for the last 15 years. And I'm also actively involved in the marketing and technical working groups of the G3 Alliance. So as Leon mentioned, I'm here to talk about the data broadcast mechanism, and in particular, talk about Trickle and the enhancements we've done for those. So just to recap on what Cedric mentioned, basically when we have very dense networks, and in particular the broadcast mechanism or IPv6 multicasting, as currently specified, each device that receives a broadcasted frame should propagate that frame at least once on the network. If we consider small networks, then I don't think this is so much of a problem. Basically, we only have a small number of repeated frames. However, if we consider dense networks, so networks 300, 400 or 600 nodes, then a single broadcasted frame can be repeated maybe 600 or 800 times in the network. And it's quite clear to see that that's quite an inefficiency. That's inefficient use of the bandwidth that we have, and also so we've been working at looking at ways to reduce these, and one of them is Trickle. So Trickle is a well-known RFC, so request for comment. I've put the link there so that anybody wants to actually go and look at the document, they can. It's a 15-page document, and if you take off the references and the authors, it's about maybe 8 to 10 pages of text. It's also a very simple algorithm, so I'd recommend anybody who's particularly interested to go and look at the document itself. It establishes basically a densely aware local communication with an underlying consistency model which guides when a node transmits. So it's a simple suppression mechanism which basically allows the trickle communication rate to scale logarithmically with density. So instead of flooding the network with packets, the algorithm controls the send rate so that each node only hears a small number of devices. It's also robust to network transients, loss and disconnection, so it's ideal for power line. And it's also simple to implement and requires little in terms of memory. So again, it's perfect for G3. So how does Trickle work? Well, Trickle is very simple, so I hope I don't complicate it. But basically, you have 3 configuration parameters. So we have an IMIN, so we have a minimum time duration, and we specify this. We have an IMAX, so a maximum interval size. Now, IMAX is usually defined as a factor of the IMIN, so a multiplication factor of IMIN. And we have a redundancy constant K, which I'll come on to in a moment. And in addition to that, we have 3 variables. So we have the current interval size, and we have a time T within the current interval, and a counter C. So one thing I should mention as well is the Trickle algorithm is basically protocol and transmission media agnostic. It basically gives guidelines to the implementers on how the algorithm should work, but it's left to the implementers then to tailor that to the particular protocol. So if we consider maybe broadband PLC, then you'd expect these broadcasted frames to happen very quickly. If we consider maybe narrowband, then obviously the delay is slightly higher, the frames aren't so quick on the network, so maybe the timings need to be adjusted basically for the protocol and the media itself. So I mentioned the Trickle algorithm has 6 rules. Again, it's up to the implementer to decide how they're used. But basically, if we consider a point here, we are looking for consistent, inconsistent, and events. And these are all given as a guide in the algorithm, but it's up to us to consider what they would be. But as soon as we hear a consistent event and we start our Trickle instance, we define a random value t as a random time interval between our Imin and Imax value and I over 2. So t varies again on each individual node, and it's a randomized value. And what we're doing is when we see a broadcasted frame, we reset a count to C to 0. And during that time period, we are counting the consistent frames that we receive in the network. So you can see in this particular instance, we have received 3 packets within our time window. And when our time value t expires, we compare our value c, our counter value, with our redundancy constant k. And if c is less than k, then we decide to transmit the frame. So you can see our redundancy constant basically applies a suppression. If we set k much higher, then obviously we need to receive many more packets within that specified time window. So if k becomes quite high, then our suppression is quite low. And if k becomes quite low, then our suppression is quite high. So it allows us to kind of factor in a redundancy constant and control the repeating and the trickle, if you like, of these frames. So as I mentioned, the terms consistent, inconsistent are up to then the protocol itself or the implementers to define. But the idea is we have a randomized time which we are collating these frames before actually propagating them to the network. So I think the mechanism is relatively straightforward. So how does G3 use Trickle? Well, we're using this for broadcasted data frames. So basically consistent transmission there for us is considering a copy of the same broadcasted frame. So it's a broadcast frame with the same broadcast contention header and the same source address. And we consider a single time interval for the broadcasted frame. So we only have one Trickle instance for the broadcast. So we create a randomized time window, and we do that for every single broadcast. If and G3 can support multiple different broadcasts in the network. So for that, for G3 is defined that a separate Trickle instance will handle each individual broadcast. And we do the same mechanism. So at the when the Trickle timer expires, we compare our C value to the redundancy constant and repeat the frames. But what we've done within the G3 Alliance is we've kind of made an adaptive K. If we look at this kind of cartography diagram, which Cedric presented at the very beginning, with G3 networks, we see generally a data concentrator point in the middle, and we might see some limited number of sparse devices which are acting repeaters in the network. But what we can also see, if you look at this area, is we have clusters of highly dense areas. So what we want to do is change the suppression mechanism based on the density of the nodes in the network themselves. So we have an adaptive KI, and basically that's based on a MAC POS recent entries. So within G3, we have a POS table, so that tells us how many near neighbors we have. So we define an attribute which is basically related to the number of POS table entries we have, which have been refreshed recently, and where the LQI is above a certain defined Trickle threshold. So that lets us control the redundancy constant within denser areas of the network, because here we would like maybe the suppression to be higher. We also have a Trickle step which helps us control that, and that gives us an indication of the desired redundancy. We also then have a Trickle max KI value, and that then defines the maximum redundancy allowed in the PAN, so that all nodes are behaving at least in a consistent manner. What we've also done in the G3 is we have other attributes. So we have the ability to set a parameter to turn on and off the Trickle algorithm, but we also have an adaptive IMIN definition. So I mentioned that Trickle itself is protocol agnostic. It doesn't necessarily define, so it makes sense, as I've mentioned, to tailor this to the media that's being used, and in this case narrowband. But what we can also see in G3-PLC, we support FCC and Senelec, and obviously the frame length and the time duration of a transmission is much faster in FCC than it is in Senelec. it makes sense for us to also have an adaptive time duration. So we do that by enabling an adaptive IMIN, and that's then specified as the time duration of a broadcasted packet. So that broadcasted packets themselves can be varying in length, so they vary in time also. And as I mentioned, FCC and Senelec has that variation. So we measure the time duration of the broadcasted packet. We multiply by our Trickle max redundancy constant. So what we need to do is at least ensure that our time window we're waiting has enough time to have heard at least the minimum number of redundant packets, and we then add a multiplication factor. If we're not waiting for enough packets, then obviously the algorithm isn't working, so we have to allow a certain minimum time frame to have received those frames. So how have we tested it? Well, the bottom diagram here, this is the test setup we have at Renesas. So this supports about 450 devices. It's based on a real world condition of a typical installation. The topology is shown on the top here. So basically we have 16 different clusters, and they're all separated by cable drums and varying attenuations between each cluster. And it allows us also to inject some noise sources into varying parts of the network. So for the Trickle algorithm, we've tested on a 330 node dense network. And what that allows us to do is to test different variables of the Trickle algorithm, or different values of the Trickle algorithm in a controlled environment before we install it, and we ensure that it works before doing field installations. And the first results actually are very, very promising. If we look at the diagram on the right-hand side, this is the default specification. So this was without Trickle enabled. And what we can see here is this blue graph. The blue graph represents an error rate. So with the specification as it was, you can see that actually that 25% of the nodes don't hear the original broadcast, or don't hear the broadcasted frame. So that's again, highlighted a need to optimize the broadcast mechanism. The orange line depicts the drop rate. So I mentioned the K factor can vary the suppression. So what we can see is, as long as the trickle timer is sufficiently long enough, so as long as we make Imax quite high, we can see the error rate is dropped in these particular cases to less than 1%. So that's a significant reduction in error, which is fantastic to see. But what's also most pleasing to see is in certain attribute settings, then the drop rate itself can be over 80%. So that's an 80% suppression of the broadcasted frames within the network. And in this particular case, 80% frames dropped with 0% error. So that shows us that the mechanism quite clearly works. And that's now included in the specification. And they can be then tested in the network in the future. So the final slide from me, I won't talk too much. This slide just lists all of the modifications to the specification. So we can see basically here is all of the headings in the G3 specification where Trickle is mentioned. So if anybody is interested, then please maybe look just at these sections, or alternatively, and probably the best way, is take the latest version of the specification and search for the word Trickle or Trickle algorithm, and you'll be able to see more. So thank you very much. I hope it's been useful. Leon, I'll maybe hand back to you.
Thank you very much, Kevin, for explaining. So I'm glad we also get quite some questions online, and we're answering them directly. So you should be able to see some questions and answers in your control box. Kevin, one question for you before we move to Greg. We talked a little bit about the impact on latency in the previous presentation. So what is the impact on latency when using the Trickle mechanism?
Yeah, again, good question. I mean, yes, by adding, similar to Matteo presented with the jittering, with the Trickle algorithm, we're adding a delay before repeating the frame. So there is an additional latency. However, I think with the results, what we can clearly see is that latency is the benefit to us is clearly the suppression in the network. obviously reducing the broadcasted frames are very congested. The congestion itself causes noise, causes collisions, is an inefficient use of the network media. So actually the additional latency, I think, is far outweighed by the benefits on the suppression itself and the reduction in the error rate. So yes, there is latency, but yeah, there's a clear advantage.
All right, thank you. So if I don't see any other questions we haven't answered yet. So if you have a question for Kevin, please enter it. Let me see here. It's a very specific question, I think. What is the recommended ADP routing table entry TTL value for a dense network, Kevin? But maybe that's a bit.
Yeah,
really
I mean,
specific.
maybe that is quite specific. I mean, I don't know whether each implement or each vendor would offer. I mean, generally for us, we recommend around 6 hours. But again, this depends on the application layer and the network itself. So, for example, if you have a meter reading network where you are trying to poll every meter within 15 minutes, then you probably want to make the time to live much shorter. But in the defaults from Enedis, the idea was to have one meter reading every 24 hours. There are other mechanisms then to ensure that the devices themselves are connected to the network. So you might have a mechanism which says if a meter hasn't heard from the concentrator every 6 hours, you need to rejoin. So what I'd say is our recommended would be around 6 hours, but that's based on a use case of polling a meter once per day or doing a load profile once per day. So again, depends on the application layer, depends on what you're wanting from the G3 network. So again, happy to take that slightly offline, but yes, it all depends on the application layer.
Yeah. In the presentation, we have all the contact details as well from all the presenters. So if you have any specific questions afterwards, you can, of course, contact any of us directly. So looking at the time, I think we should move on to the next presentation, the last presentation before we have some time to discuss. So I'm handing to you, Greg. Let's see if it also works in all the way from Taiwan.
Yeah. So can you hear me?
Yeah, I can hear you.
And can you see my screen?
Not yet. Yeah, there it is. Perfect.
Okay, good, perfect. Okay, can I start now? Okay, good morning, good afternoon, everyone. I'm Gregson, the senior engineer of software development department in VertexCom, and I have over 13 years experiences of developing embedded software, especially for wireless communication and IoT portable stacks. So today I'm going to introduce a new mechanism, class head forwarding scheme in the latest G3-PLC specification, which provides performance enhancement in dense networks. So this new mechanism adapts two techniques which are already presented today. One is the jittering and another one is Trickle. So when the jittering is enabled, ideally for route establishment procedure, every node in the network still has to forward the REQ message at least once. So for large scale and the dense networks, the number of REQ forwarding still can be very large. So we need to use another technique, Trickle. So for dense networks, maybe just like this figure, which usually consists of clusters of nodes, and it would be sufficient one or few nodes of each cluster forward the REQ message. And how can we make it? We need to define an appropriate consistent event. So as long as the consistent event happens enough to a given node, then this node can suppress the RIQ message forwarding. So what is the consistent event of the Trickle algorithm we are using in this new mechanism? For a given node, if the received RIQ message is from the same cluster, and this received REQ is similar to the buffered REQ message received before, then this received REQ messages is regarded as a consistent event. So if the received link quality is better than the threshold, this received message is regarded to be from the same cluster. And when there are two REQ messages, including the same hop count value and the same weekly count value, and the difference of their row cost values is in a specified range, then these two REQ messages are regarded to be similar. So take this figure as an example. So there is look at this green cluster, and when this cluster receive this REQ, so every node in this same cluster most likely forwards the similar REQ messages. You can check the hop count value; they are the same, and weekly count value are the same, and their row cost basically is in a very small range. So I'll go through the algorithm briefly here. For a given node, when the received REQ message is the first one or a better one, this node needs to update the buffered REQ and reset a variable cluster counter. Then, if this received REQ message is the first one, we need to start a timer for forwarding it with expiration T delay, which is computed according to jittering. If the received REQ message is not good enough to replace the buffered one, we need to check if it is a consistent event. If it's a consistent event, this node needs to increment the variable cluster counter. So after the timer is expired, this node needs to check the variable cluster counter. If this counter is less than the threshold ADP cluster trickle K, then this node needs to forward the buffer REQ. If this counter is not less than this threshold, this node can discard this forward REQ. So this is how this algorithm reduce the REQ message traffic. So based on the algorithm, Vertex.com did some tests to verify this algorithm in our lab. And this is the test topology. There are totally 301 nodes, and one of them is the coordinator. The rest of them are regular devices. And we use 50 dB attenuators to make 8 ranks to simulate a cluster scenario. And based on this test environment, we also design different configurations. So the first configuration, for this the configuration, we only enabled jittering algorithm, and the other configurations we enabled jittering and Trickle with different parameters. Then let's look at the test procedure. So after bootstrapping, the coordinator pins each node in the network one by one. And in order to trigger the route establishment procedure, the coordinator needs to clear the routing table before starting to issue the pin request to each node. So after pin operations, we need to collect some information for analysis. They are the total number of REQ forwarded by each node, the route cost from each node to the coordinator, and the success rate of pin operation. So let's look at the test results. So in this figure, on the x-axis, every point represents the node in different ranks. Okay, and on y-axis, it tells you how many REQ message forwarded by each point. Okay, so and the green line here, the green line represents the jittering only configuration, and other colored lines represent configurations of enabling jittering and the Trickle. So from this figure, you can see enable Trickle algorithm leads to significant separations of forwarded REQ messages compared to jittering only configuration. And this separation is getting larger for the nodes in high ranks. Then these figures shows the average of REQ messages forwarded by each node for different configurations. The same, this color is jittering only configuration. So for jittering only configuration, on average, every node needs to forward 802 REQ messages. And if we enable jittering and the Trickle algorithm, we can see that on average, every node at most only needs to forward 108 REQ messages. So there is 86% separation of REQ traffic. That's huge. Then this figure shows the average route cost from each node to the coordinator in different ranks. Okay, and you can see that enabling Trickle algorithm does not increase too much route cost. Okay, in the meantime, the REQ traffic is reduced a lot. Okay, then this figure shows the success rate of pin operation, and you can see that all configurations can provide sufficiently high success rate of pin operation. Then what's the conclusion here? Our new mechanism cluster forwarding scheme adapts jittering and the Trickle to concepts. Jittering, as presented by Matteo, it can lower the flooding issue. And Trickle can gain extra benefits extended from jittering. And from the test results, we saw huge reduction of RIT traffic and suboptimal role establishment and high success rate of communication. So we can say that the communication quality can be maintained when a cluster head forwarding scheme is enabled. Yeah, so that's it. Thanks for listening.
No, thank you very much, Greg, for explaining and sharing your lab results with all of us. There was one question from Roman. What is it? Ranks? I don't completely understand the question. Maybe Roman, you can clarify a little bit. Or Greg, do you understand?
Okay, ranks. The ranks here I mentioned, actually I want to make each rank as a cluster to simulate a cluster scenario in real world. Because in each cluster or rank, if we don't use the Trickle and jittering, every node in the same rank in the same cluster is to forward the IQ message. That's a lot of traffic. And the rank also, the rank means how far the nodes they are to the coordinator. Like rank 1 is just 1 hop to the coordinator. Nodes in rank 4, they are 4 hops to the coordinator.
Ah, okay.
Yeah.
All right. I see. Thank you. So that is the presentations we prepared. So we still have time for questions. So if you have any further questions, please put them online, and then we will address them. And they can be more generic if you want, and not have to be related specifically to the presented topics. One of the questions we received up front is more generic, I think, and Cedric, maybe you can start answering. And the question is, what is the recommended practice in case of crosstalk when 2 data concentrators are visible on the G3-PLC network?
Yep. Yeah, indeed, a good question. I think that there's 2 things to consider in this question. I mean, crosstalk on the communication problem, at least with G3-PLC, which uses CSMA-CA channel access scheme, is not an issue, because basically there's no synchronization between networks, something like this, that will create trouble when packets are sent throughout or on channel. So from that point of view, there is no issue. I would even say it could even be seen as an opportunity, as a neighboring node that is better heard on the neighboring network could repeat a message towards the original network. So that's the answer from the communication point of view. It's not an issue. Then, of course, it might be an issue from a utility perspective, as you would like to have given concentrators and meters that are being operated within same grid. Well, this is true, but at the time being, there is no real way to deal with that in the lower layers. Nevertheless, what could be done, for example, is to have, if you want to force a meter to be connected to a certain data concentrator, you might use application layer mechanisms such as blacklists or whitelists that can force some behavior. But of course, you have to be sure that that you can communicate correctly within each network.
Does anybody? So thank you, Cedric. Does anybody want to add to that, or is it a complete answer already? I think it was pretty complete already, the answer. Huh? Cedric, another question maybe you can address. Huh? That's about deployment and optimization of G3-PLC infrastructure and the enhancements.
Yeah. Yeah, so basically, well, as we depicted here, the alliances, the G3-PLC alliance is working on the different topics, issues that come from the field along the time. So this way we ended up with 2015, 2017, and now 2021 specifications. So of course, for these enhancements that were just presented, they will be in the certification program end of this year. So obviously, they have not been implemented in the field today. Return and experience in the real field still need to be gathered. And I would just add that at the time being, the features are disabled by default, and then when some end users decide to test it, and some of them are involved in G3-PLC alliance, this could of course help us to refine the default parameters. You always need to go step by step, and at the end we can then again in, I don't know, 2022, 2023, come up with dedicated parameters that would let's say consider return and experience.
All right, thank you, Cedric. Another question we received just now. Are there some disadvantages and negative effects of the proposed algorithms? This is a question which just came up over the system. So are there some disadvantages and negative effects of the proposed algorithms? I think we already talked a little bit about the implications potentially for latency.
Yeah, so maybe Leon, if I take that, so I would agree. I mean, latency is one of them, specifically in the jittering. And when Matteo mentioned the delays can be up to maybe 1 second per hop. Certainly in the Trickle algorithm, then we've mentioned you have to allow a certain amount of time to have heard all of the frames within your redundancy constant. So the time delay itself has to be sufficiently large. Other negative effects, I mean, some of the things we've seen while doing the optimizations itself is the algorithms as well work well in particular areas of the network. They work very well with clusters with larger devices, and maybe they don't necessarily work so well where you have maybe single hops or lines. So I think it's clear, certainly from the Trickle point of view for broadcasting, there are some drawbacks, and I think it's a case of actually now working on coming up with a good set of parameters which work well in all the field installations and all the different topologies. I don't know whether maybe Matteo and Greg have the same experience for jitter and jitter and cluster forwarding, but
yeah, you're right, Kevin. Let me just add that we are talking about enhancement for dense networks. So of course our testing was also focused on networks with a large number of devices. In that case, we detected a limited number of disadvantages. So we are not so worried, let's say. Of course, if we apply the same improvements on a very small network, we don't see the benefit we presented today, for example. So the benefit of using Trickle or using clustered in a small G3 network, maybe made of 10 or 20 or 30 nodes, probably it is not worth.
Yeah. Thank you for adding that, Matteo. And another question we received, and it's not specifically related to the topic today. It's related to the frequency hopping. The question is, how will frequency hopping be used in the future on the G3-PLC hybrid? Matteo, maybe you can.
Yeah. Okay. the G3 Alliance, the workshop one in particular, is actively working on frequency hopping definition, and we expect to have a first version of specification ready for the end of this year. So the frequency hopping has mainly two goals. The one is to be able to respect regulation on given for given installation for given countries, and the second goal is to exploit the advantage of transmitting on different RF channels. Of course, if we can exploit different channels more or less in a random way, we could avoid the noisy channels, or we can, or if there are some noisy channels, the probability that they affect the communication is lower with frequency hopping. So we are working on its definition, and in our idea, the use of frequency hopping, it will be transparent for the user point of view. Let's say it will be embedded in the G3 stack, in the G3 protocol, and it should be transparent for the end user.
Yeah. Thank you, Matteo. Anybody wants to add to that? I think Cedric already mentioned in the beginning. It will be included in the specification end of this year, and it will be included in the certification release in 2022. And the timing for that certification release is to be determined specifically. But anybody who wants to add to the frequency hopping question, maybe? No? Then there was also a question we received very recently, and Kevin, maybe you can help with that one. It's also about the hybrid solution integrating the RF channel. And the question is the 169 megahertz one of the RF frequencies that's going to be integrated in the solution?
Okay, I mean, I think the simple answer to that is currently it's not on the roadmap. But I'd say one of the ways we're working within the Alliance is certainly the focus when we introduced the RF mechanism was on 868. So the frequency bands used within Europe. But what we're looking at, certainly within the Alliance and the CPEC within the G3 Alliance, so in WS1, the technical working groups, is we will then work to support any of the RF frequency bands, provided there's a sufficient use case or there's justification within the Alliance. So if somebody has a particular need for 169, then as long as they're an Alliance member, that they have the opportunity to propose it. And if it makes sense and it's possible technically, then it's something that the Alliance will consider. But one of the negatives, if you like, of RF and all the different worldwide frequency bands then is the certification profile and the complexities of guaranteeing that every single frequency band works. So that's why at the moment it's a limited set, but basically the Alliance is working now quite hard on opening those up to many different frequencies other than 868, so 915 for Americas and other regions.
Yeah.
And we seem to have lost others. I don't know.
Well, we're still here, and I'm pretty sure the attendees are still there as well. So let's not be distracted. The same question related to the hybrid. What RF protocol was used? I think you can see the question on the screen as well.
Yeah.
So the RF protocol, I mean, G3 is not using an RF protocol as such. So what we've done is we've taken an RF lower layer. So what we've defined is the 802.15.4 Sun FSK as the RF mechanism that supports many different frequency bands. So I've mentioned 868 and 900 megahertz. So that stays the same, if you like. The RF mechanism as defined in 802.15.4 And we use the same MAC layer. So G3-PLC, the PLC part is based around 802.15.4 MAC, but adapted to a powerline media. We use the same in G3 for the RF side of things. So we use the 802.15.4 MAC layer for the RF. The integration is done at the sort of the load NG, which is the G3 protocol as such. We have the adaptation layer and then the routing. So as Cedric mentioned and Matteo mentioned, the load NG is the routing protocol. So as such, it's not an RF protocol in its own right. It's an extension of an RF medium, which is very similar to the PLC medium. So they're both based on 802.15.4 MAC with a load NG routing protocol on top of both. So the idea is the device can propagate route requests, as Matteo explained, on both media at the same time, and then it can choose the best route, and that route doesn't have to stay on that media. So each hop within that route can be based on PLC or RF, and it can switch per hop as it propagates through the network.
Yeah, thank you, Kevin, for explaining. There was another question from Bin Vu in Vietnam. Does G3-PLC support 125, 132, 406 kilohertz? There, the same answer applies as we mentioned for the 169 megahertz. Currently not on the roadmap, I know. Kevin, you want to add? Or Matteo?
No, when I read the question, I thought they were talking about PLC frequency, so thank you.
Well, you may be right there. You may be right there. Yeah.
Yes, because they are killers.
Yes. Yeah, my mistake.
Oh, okay.
It might be a question that, I mean, it could be maybe be clarified, but I think it might be a question about subbanding. But for sure, I mean, we consider different band plans between basically 35 kilohertz and 400 and I mean almost 500 kilohertz. We have the Senelec A band plan, so OFDM modulation between 35 and 90. Senelec B, I think it stops around 125 kilohertz, if I'm not wrong. And then we have RIB and FCC, which work in the upper frequency band from 154 kilohertz up to 487 or 450 for RIB, I think, if I'm not mistaken. So it's really a full OFDM bands. It's a multi-carrier technology. So there is no specific use of only 125, 132, or 406 carrier. If I've rightly understood the question. I don't know if my colleagues would like to add something about that. Hopefully I've answered.
Well. Yeah.
Okay, so I hope that answered your question, Bin Vu. And another question, maybe Cedric, you can help with that one. How should the firmware take place which supports a newer set of ADP attributes?
I think the question is how should you make the firmware updates? Well, I'm not sure I totally understand the question, but maybe what is meant behind is that you have a certain configuration of your G3-PLC network at the time being, for example, 2017 firmware with the certain setting of the different attributes. So of course, then if you want to switch to 2021, you would then, I mean, the typical firmware update procedures would be to send the firmware to all the meters, and then at a certain time to activate the firmware and the whole network. At least this is one deployment strategy. And then I think you should not encounter any issues with inconsistent ADP attributes. But that's what I understand behind this question.
All right. If I hope that answers. If not, then please contact us. Let's take a final question, I think, before closing this session. It's again about the hybrid solution. Kevin, maybe you can help with that one. Huh? The question is, in the hybrid, is there a way to force a specific path for the RF communication? For example, a direct point-to-point connection.
That is a good question. I mean, in particular with LoadNG, I mean, LoadNG has a very powerful composite metric. So that lets you tailor some of the choices, if you like, of individual links. It's probably possible, and again, maybe I'd like to take this a little bit offline later, but it might be possible to configure some of those attributes in some of the LoadNG routing cost to force an RF link and to force it between two devices. I would say that's not really what the mechanism was designed for in G3, if you like. That the idea was to choose the best media per hop, but that's not to say that it wouldn't be possible depending on the use case. So G3 is very powerful. There's lots of attributes. There's lots of different ways to configure, certainly things like the routing cost metric. So generally, it's possible to tailor it to a different application.
Yeah, yes, maybe Kevin, if I can add something. There is also room for some customization for each implementation. So there are also some attributes in order to switch off and on the PHY layer or the RF layer. So it is possible for an implementation to select maybe a link to be always in PLC or in RF. Yeah, as you said, it is not the normal use we are thinking of when we talk about hybrid, but I think it can be done.
Okay, thank you. And if we need to further discuss, we can take it offline and answer directly, maybe. So we're getting to the end of the session. It's been quite technical, but we also were able to answer a couple of more generic questions about G3-PLC. So I hope that has been useful to you. So I want to thank all of you for attending today's session, and especially thank you, Cedric, Matteo, Kevin, and Greg for presenting the technical topics today. Like I said, if you have any further questions that you would like to discuss, don't hesitate to contact any of us. The emails are in the presentation. And like I mentioned already, we will share the presentation with all of you and make the recording available as well. So thank you. Hope to see you again in another webinar, or hopefully in Milan, in NLED Europe, for example. So thank you, and good day.
Thank you.
Thank you.
Thank you.
Bye.
For listening. Bye-bye.
Bye-bye.